In modern data science, generating machine learning code is no longer the true bottleneck. Even as AI tools auto-populate training scripts, banking dashboards continue to flash red with millions in active fraud losses. Expertise requires translating abstract statistical metrics into concrete business logic to prevent these costs. Consider an automated fraud detection model reporting a 99% accuracy rate. On paper, it is a success. Yet the bank continues losing money to hackers every day. This happens because of the math of an imbalanced dataset. If 99% of transactions are normal and only 1% are fraud, a dumb model that simply predicts normal for every transaction will achieve 99% accuracy. That model has zero utility. It misses every single attack because it was never tuned to find the minority class. Relying on top-line accuracy for imbalanced data creates an operational liability. To build a working system, engineers must look past basic predictions and analyze the underlying probabilities. Algorithms like logistic regression or XGBoost do not natively output yes or no labels. Instead, they output a confidence probability between 0 and 1. By default, the algorithm uses a decision boundary set at the 0.5 mark. Any probability score above 0.5 is assigned to the positive class, while anything below is assigned to the negative class. This 50% default is an arbitrary mathematical assumption. It is not a rule dictated by the needs of the business. Engineers manipulate this probability threshold to dictate how the model behaves in the real world. In a spam detection scenario, the cost of a false positive is high. If a legitimate job offer is incorrectly flagged as spam, the user misses a critical opportunity. To prevent these expensive false alarms, we must demand higher confidence from the model before it labels an email as spam. By raising the threshold to 0.7, the model must be 70% confident before flagging an email. Precision rises and false positives drop. This improvement comes at a cost. Demanding higher confidence means missing actual spam, causing false negatives to increase. Contrast this with pneumonia detection. In this scenario, the cost of a false negative, completely missing a sick patient, is absolutely catastrophic. In a medical context, we lower the threshold to 0.3. We only require 30% confidence to trigger a clinical review. Recall spikes to maximum. Catching every real case ensures an increase in false alarms, forcing healthy patients to undergo unnecessary secondary tests. Shifting the decision boundary is a zero-sum trade-off. The final setting is dictated by the financial or human cost of the specific problem. Manually testing individual thresholds is a slow process. To find the optimal balance, we need to map out every possible boundary at once. We create a map comparing the true positive rate against the false positive rate. The software calculates these two rates across every possible probability threshold, from 1.0 down to 0. Plotting these continuous points forms the receiver operating characteristic, or ROC curve. Area under the curve, or AUC, provides an aggregate measure of model performance. It represents the total two-dimensional area beneath that plotted line. A perfect model has an AUC of 1.0, pulling the curve to the top left. A useless model has an AUC of 0.5, represented by a diagonal line indicating random guessing. The ROC AUC is the definitive engineering map for translating probability into business action. Consider an enterprise problem involving IoT sensors. These sensors detect hardware anomalies, but human staff must physically review every flagged event. The client demands a recall rate above 90%, ensuring no real hardware failures are missed. The ROC curve shows achieving 95% recall drops a dotted line to the 30% mark on the false positive axis. In business terms, this 30% rate means reviewers spend $45,000 a month investigating false alarms. The client rejects that cost and demands the false alarm budget be reduced to $5,000 a month. To meet that budget, the false positive rate must drop from 30% to 10%. At a 10% false positive rate, the curve shows that recall drops to 80%. The team extracts the exact probability threshold of 0.6 from these coordinates and hard-codes it into the production deployment. The ROC curve provides the specific coordinates needed to settle the financial negotiation. Before deployment, we must confirm that the 0.6 threshold is mathematically robust and not just a result of the specific data used for training. Relying on a standard 80-20 train-test split is risky when dealing with highly imbalanced data. A random shuffle could leave 0 fraud cases in the test set, making it impossible to evaluate the threshold accurately. Stratified K-Fold cross-validation solves this by dividing the data into 5 equal folds for testing. Stratification forces every fold to maintain the original class distribution. This guarantees a consistent test environment across all evaluations. Out-of-sample validation through stratified K-fold is required before any threshold is trusted for live deployment. In the production environment, the model becomes a live, active inference endpoint, continuously receiving a constant stream of real-world data. The live environment is not static. New hacking tactics emerge and macroeconomic conditions shift, changing over time. When live data deviates from the historical data used during training, the model experiences data drift. Data drift can physically alter the ROC curve, invalidating the 0.6 threshold and increasing business costs. Constant monitoring and feedback loops are necessary to catch these performance drops before they impact the bottom line. Building these systems requires an operational engineering lifecycle to defend the model's business alignment.